In this video, I will define the DTFT and its inverse. The input to the discrete time Fourier transform is a discrete signal. The operations of the DTFT are as follows. The summation from n equals negative infinity to infinity of the input multiplied by e to the negative j omega n. The output of the DTFT is usually denoted by a capitalization of the input variable with argument e to the j omega. This notation can be a bit confusing when you're first wrapping your head around the DTFT. The variable of the output is omega, not e to the j omega, as e and j are both constants. It is the convention to put it in this form to remind ourselves that the input was discrete and not continuous. The output of both the continuous time Fourier transform and the discrete time Fourier transform is continuous in omega. For me, this has been one of the main sticking points on the road to intuition. The inverse DTFT has the following form: 1 over 2 pi times the integral over a 2 pi interval of the input times e to the j omega n. The integral is with respect to omega. The 1 over 2 pi can be thought of as a normalizing factor required when moving between continuous and discrete domains. To convince ourselves, let's derive the IDTFT from the DTFT. Start with the definition of the DTFT. X of e to the j omega is equal to the sum from n equals negative infinity to infinity of x of n times e to the negative j omega n. Multiply both sides by e to the j omega k. Then bring the e to the j omega k into the summation. Let m equal k minus n, which means that k minus m equals n. Swap these definitions into our equation. Integrate both sides of the equation over a 2 pi interval with respect to omega. Assume x of k minus m times e to the j omega m converges so that we can pull the summation out in front of the integral. Here, we note that the integral of e to the j omega m over a 2 pi interval is equal to 2 pi if m equals 0, and 0 for all other values of m. This means that the right-hand side equation only needs to be evaluated for m equals 0. Otherwise, we're just summing a bunch of zeros. So, plug in 0 for m and simplify the right-hand side to 2 pi times x of k. Divide both sides of the equation by 2 pi, and we are left with the inverse discrete Fourier transform.